chào tất cả các em. Hôm nay thầy của chúng ta sẽ đi về chuỗi bài giảng tích phân trong chương trình giải tích lớp 12. Trong chuỗi bài giảng này, thầy cùng chúng ta sẽ tìm hiểu một số nội dung sau. Nội dung thứ nhất là về nguồn gốc và ý nghĩa của phép tính tích phân. Nội dung thứ hai là các tính chất của tích phân. Nội dung thứ ba là các phương pháp tính tích phân. Nội dung thứ tư là ứng dụng của tích phân, và nội dung thứ năm đó là củng cố và cập nhật các dạng toán tích phân trong đề thi Trung học phổ thông quốc gia những năm gần đây. Và trong video này, thầy cùng chúng ta đi tìm hiểu phần 1 về nguồn gốc và ý nghĩa của phép tính tích phân. Và trong phần này, thầy mời các em xem một trích đoạn trong bộ phim Mathematical Universal nói về nguồn gốc và ý nghĩa của phép tính tích phân với phụ đề tiếng Việt. Mời các em cùng theo dõi.
After centuries of brilliant attempts, a general method for computing areas of curved shapes was achieved in the 17th century. That method is called integration.
It's often been said that Isaac Newton was born in the same year that Galileo died, as if it were necessary to have one person of that caliber on Earth at all times.
When Greek traders asked questions about specific areas and volumes, Greek mathematicians were able to offer specific answers.
The area of a rectangle is the product of its base and its altitude. A triangle has an area half that of a rectangle with the same base and altitude. Any plane figure, bounded by polygonal lines, can be divided into triangular pieces, which makes its area the sum of the areas of all the pieces.
But how does one find the area of a curved figure, a parabolic segment, or an even more exotic shape? These mathematical questions were challenges to the mind and spirit of Greece. In an intellectual marathon, which may be thought of as a relay race toward the calculus, Greek mathematicians competed to find a general method of quadratures, a process for calculating areas of curved figures. There were strong entries from other cultures, but the first lap was a victory for the Greeks. Their idea was to approximate the curved figure with inscribed polygons. Attempting to exhaust the whole figure, bit by bit, they used an increasing number of sides. This ancient Greek approach is called the method of exhaustion. He called it the method of fluxions. Newton saw that the rate of change of a function gives the slope of its graph, and realized that the slope itself generates a new quantity, the fluxion. Today, Newton's fluxion is called a derivative. This mathematics was stronger than the Greeks. Leibniz's was slightly different from Newton's, and in some ways, slightly better.
Leibniz incorporated the idea of calculating area by imagining a picket fence of little rectangles. Imagine them diminishing in size and add their areas. Eventually, their sum approaches a limit, which is equal to the area of the region under the graph of a function. This is the process of integration. Leibniz summarized it with the integral sign, an elongated S from the Latin word for sum.
Both Leibniz and Newton, each a genius with a new idea, recognized something the others had overlooked. They saw the surprising connection between integration and differentiation. This remarkable connection can be understood by calculating the area of a parabolic segment.
Let A of t denote the area between the parabola and the x-axis, from x equals 0 to x equals t. This is a function of t. Try to find its derivative, dA dt. If the area from 0 to t is a of t, then the area from 0 to t plus delta t is a of t plus delta t. The area delta A is the same as the area of a rectangle of base delta t and height x squared for some x. As delta t shrinks to 0, x squared becomes t squared. In other words, the derivative of the area function is t squared. Trying various functions to see which one has t squared as its derivative, 1/3 t cubed eventually comes to mind. That works. And so does 1/3 t cubed plus a constant, because the derivative of a constant is 0. The area function a of t is 1/3 t cubed plus a constant. Since the area is 0 when t is 0, the constant is also 0.
So there it is, the quadrature of the parabola, using the calculus of Newton and Leibniz. In the language of calculus, the integral of x squared from 0 to t is 1/3 t cubed. Of course, Archimedes had already done this by a geometric method, but the calculus is superior. Calculus applies not only to the parabola, but to any smooth curve. It solves the problem of quadrature in general. Since the derivative of velocity is acceleration, velocity can be obtained by integrating the acceleration. And since the derivative of displacement is velocity, displacement can be obtained by integrating the velocity. Newton was aware of the profound power of this new mathematics. But as he sat polishing his calculus as if it were a most precious apple, all the while posting cryptic hints of its golden flavor, Leibniz published his differentials and integrals. 3 years later, Newton somewhat reluctantly published his mathematical principles of natural philosophy, the Principia. And yet, except for a few hints, Newton kept his calculus to himself. While Newton remained secretive about his work, the same could not be said of his countrymen, who praised him at the expense of Leibniz. They created chaos in the Royal Society over the matter of who first invented the calculus. The Newton-Leibniz controversy was bitter in taste and mean in spirit. One of its low points was the charge that Leibniz had plagiarized ideas from Newton's letters. Leibniz was outraged and demanded a formal hearing. Of course, since Isaac Newton himself was president of the Royal Society, Leibniz might have made a wiser move.
This has come for you by hand, sir.
Oh, thank you, George.
Even before pleading his case, Leibniz was judged guilty.
The messenger would know if you wish to send a reply.
No reply.
Thank you, sir.
And so, Leibniz, who'd begun his career in mathematics with the philosophy of optimism, ended it with an equation of bitterness. Hearing of the German's death, Newton boasted, "I had broken Leibniz's heart." Ironically, though Newton's fluence and fluxions were to rule Britannia for a century thereafter, Leibniz's notation was better, and it became the universal language of mathematics. His symbol for the integral conveys a sophisticated idea. The integral is the area of the region under a curve, and at the same time, it's an antiderivative. And so, the race for the calculus that began in ancient Greece finally ended in a controversial photo finish. There could have been more than enough glory for both winners. But while the glory wasn't shared, the prize was. Not between Newton and Leibniz, but among every generation since. The insight of Leibniz and Newton, most notably the connection between differentiation and integration, has evolved into a tool of incomparable value in mathematics. Thanks to both Leibniz and Newton, differential and integral calculus are the collective language of science.
First published in this book, which, as you can see, is called The Method of Fluxions. It's about Isaac Newton's theory, but it's not written by Isaac Newton. It's written by this man, John Coulson. For reasons that are not entirely clear, Newton's own manuscript about his calculus was never published during his own lifetime. It may be that he just got the manuscript ready, handed it over to the publisher, and then the publisher was a little slow in getting it out. That sometimes happens. In any case, it did finally come out. It came out in 1969. Newton's fight with Leibniz over priority for the calculus was by no means the only fight that he had during his lifetime. There were many of them. Newton was a great genius, but he was not a very nice man. One of his most famous quotations was, "If I see so far, it's because I stand on the shoulders of giants." He may have stood on the shoulders of giants, but he trampled on quite a few other people as well. I'll see you all next time.